gems, punctuality beats perfection. Since perfection waits for the right time, it never shows up. And punctuality shows up every day and conquers everything via persistence. Kudos to you for showing up to yet another grind for BITSAT 2025. This is the question bank series, and we are getting 10 questions stronger with every episode of this series. Today we are discussing question bank number 7, which means we are discussing the chapter of gravitation. Previously we have discussed question banks for chapter 1 to 6 of 11th standard. So if you have missed out on those, you can surely check it out. Once you finish with this one, it will be available in the playlist section. Now the followers of this series know the trend. Firstly, we discuss the previous year question weightage across the different topics in this chapter, so that we know which questions and which topic are questions being frequently asked for BITSAT. Okay, so let's study the previous year trend for gravitation. So from law of gravitation, we have 3 questions being raised. So basically F is equal to gmm by r square with a negative sign. Then we have questions from gravitational potential, potential energy, the potential due to a sphere, and the field inside a sphere, outside a sphere. You are supposed to know all those formulae. So the questions that came from sphere were basically based on those formulae. Okay. Then we have satellite type of questions, which we'll practice in this session. Okay. Then questions, so 9 questions from there. Important topic, gravitational potential energy. Okay. Then we have acceleration due to gravity, which depends upon height, depth, and also your angular speed, right? So questions were framed on that too. 4 questions we have from there. Then we have questions on escape velocity. We'll look into that also. We have 3 questions in the previous years. Then Kepler's law, we have 3 Kepler's law and 3 questions from there, interestingly. Okay, so that's the previous year question weightage. So let's battle out with the questions now. Question 1 and 2 for the day. In question 1, we have 2 particles, one with mass m and the other one with mass 4m. They are separated by a distance r. Okay, so you are supposed to find their neutral points. Neutral point is basically a point where the field becomes 0, right? This will have some gravitational field attractive, right? This will also have some gravitational field. Okay, so at certain point between them, the field will become 0, right? This field will cancel that field. Okay, so let's consider a point about here. Okay, I'm considering it closer to x, and by the answer that we find, it will be closer to x, and do let me know the reason in the comment section. So this x, at this point the field will become 0. Okay, or equivalently you can say force becomes 0. Okay, so now we can equate the magnitude of the field at this point, right, due to this mass and this mass. Okay, so we'll equate the field due to mass m and the field due to mass 4m. Okay, at this point x, both the fields are equal, they cancel out, hence it is the neutral point. Okay, so field due to mass m, you can relate it if you know electrostatics, it is kq by r square, right? So here it is same thing, gm by, so m is small, so gm, so in place of q you have m and distance is x square, right? Gm by x square due to mass m. Now due to mass 4m, this, what is this distance? It will be r minus x. Okay, so here we will get g into 4m by r minus x the whole square. Of course negative sign, you can cancel it out on the both sides, and g and m gets cancelled. So what do you get? R minus x the whole square is 4x square, right? So we can solve this quadratic, or we can take root on both sides. R minus x will give you plus or minus 2x, right? So we'll consider the positive solutions only, since we consider this as 0, right? This is 0, this is all the distances are measured from m, right? So we'll consider only the positive, or if you want to take both, let's take both. Okay, we'll see what happens. So if you want, if you are interested in that, so let's take positive first. So 2x plus x is 3x, so x is r by 3, which will be your answer, right? R by 3. Okay, so that is the neutral point. But if you also take the negative solution, what will happen in that case? We'll have negative x. Okay, so this will be minus 2x plus x minus x. So we get one more point, right? And this is a quadratic. Of course we are supposed to get 2 solutions, and that minus r, right? This x is minus r, right? So it will be somewhere over here. So here also the field will be 0, but we are only supposed to report one of the values that is in between them, okay? The neutral point in between them. Of course, there are neutral points over here, okay, on this side. One neutral point will be there, which we have found. And will there be a neutral point here? That is one more question for you to answer in the comment section. Okay, so you are supposed to report this value. So we have that, right? So let's come to question over here. We have the gravitational potential. We are asked for the gravitational potential energy to create a system like this. So we have an equilateral triangle of all sides L. Okay, so you are going to bring masses. So firstly you are going to bring this M, then this M, then this M. Now what is the potential energy basically to construct such a system? So basically it's the work done, right? Basically when you bring this mass, first mass M, there is no field, right? There is no field present initially. So you bring this mass M in the presence of zero field basically. So no work is done. So no potential energy. Okay. So U1 is 0. So if you want to bring this mass M from infinity to this point, no field is there. So no potential. Q into V, right? So potential is there is no field. So next, if you want to bring the second mass, now if you are bringing the second mass, this mass is present, right? We have brought this mass first. Now we are bringing this mass. So this mass is present, and we want to bring the second mass at a distance L from this mass. So there will be some potential energy. It is given by, if you remember in analogously, your in the electrostatics you have k q1 q2 by r square. So here you have with a negative sign, since it's attractive, g m, so m square by r. Okay, so this is the potential energy to bring this mass. Now we are bringing the third mass. Okay, third mass. So it is at a distance of L from this, also at a distance of L from this. Now there are two fields present due to this mass and this mass. So due to this one, we have again gm square at a distance of L, right? Then we have also this field, right? So due to that, gm square by L. Okay, so if you need the work or the potential energy for the system, you just add these three potential energies. So U total will be equal to 1, 2, 3, right? All three are equal. So 3gm square by L square. Okay, basically potential energy is the work done in bringing those masses to that particular configuration. Okay, so that's about this question. Option D is your correct choice. Let's move to the next set of questions. 3 and 4 over here. In question 3, we are supposed to find the depth at which the acceleration due to gravity becomes 1/nth of its value at the surface. So basically you'll know the variation of gravity, acceleration due to gravity with the depth, right? It is g prime is g into 1 minus d by r, right? So I'll urge you to remember this formulae for acceleration due to gravity for its variation due to depth, height, and also angular speed. Okay, so this formulae questions can be directly framed from there. So here you'll see g prime will be g by n, right? 1/nth of the value at the surface. So g is the value at the surface, and 1 minus d by r. Okay, r is the radius of the earth, right? So g and g will cancel. We are supposed to find d. So d will be, let's take this to the other side. So d by r is 1 minus 1 by n. Okay, so take the LCM. So d by r, or r I can take directly on the other side. So this will be n minus 1 upon n. Okay, which matches with option B, right? R into n minus 1 upon n. So that is the depth at which such is the case. Okay, at which g becomes g by n. So let's come to question 4 now. We are supposed to tell the escape velocity if the radius and density of the planet are given. Okay, we are supposed to tell how it's proportional to the density and the radius. Okay, so you might know the formula for escape velocity. It is not always this, okay, under root 2 gr. Since it is from the surface of the planet, this is valid. Okay, we'll learn the concept of escape velocity in the subsequent questions. It need not be always under root 2 gr. Since it is from the surface of the planet, this formula is valid. It's only valid when you launch an object from the surface of the planet. Okay. Then I'll request you to remember this form, because gr square is gm, okay, or gm is gr square. So you can substitute for g, okay, it will be gm by r square. This is a more useful form, since usually they'll give you the mass of the planet, like here they have given you density and the radius, right? But they won't prefer giving you acceleration due to gravity of a certain planet, right? G for a certain planet will not certainly be given. So you can remember this form that I'm going to derive now. B is under root 2, and G, in place of G we can substitute this. This is a constant mass of the planet usually given, and here we can find the escape velocity in a better way, right? So gm by, so you can directly remember this as one formula, but remember it is only valid when the escape happens from the surface of the planet. Okay, so I hope this is correct. Okay, so now let's substitute for mass in terms of density, since we are supposed to know the relation in terms of density. So mass is density into volume, right? Because density is mass by volume, so mass is density into volume. Now volume, you can write it in terms of, let's consider it as sphere, right, planet. So here we'll have 4 upon 3 pi r cube, right? So we'll substitute this over here and we'll obtain the relation. Okay, so actually I can drop the constant, but let's keep it. So we'll have g into density into 4 by 3 pi r cube, right? And we'll also have r, simple r. So this will become r square in the square root sign. So basically you can see, we can drop the constant now. You can see it is proportional to the square root of density. All this is constant, right? 2g 4 by 3 pi constant. Okay, and r square in the square root we have, so we can bring it out as r. Okay, so here I've used capital R, but it should have been small r. Okay, take a note. But this is the correct choice over here. Okay, under root of the density and directly proportional to the radius. Okay, so that is your correct choice. Over to the next question. So question 5 over here. In this question we have a planet orbiting in an elliptical orbit, and the sun is over here, and you are supposed to find the ratio of the momentum of planet at the point A and B. Okay, so what can we do over here? We can use Kepler's law, right? Since aerial velocity is constant, or the central force, since gravity is the central force, the angular momentum is conserved, right? So you can write the angular momentum at A is equal to angular momentum at B. Okay, so angular momentum at these 2 points will be the same, and we can find, since we want to find, what we want to find is P1 by P2, right? And we'll have, basically this will be proportional to velocity, right? So V1 by V2, but we want it in terms of R. Okay, we don't want it in terms of V. Okay, so we'll have to find how is this V related to R. Okay, and that we can do using angular momentum. Okay, so I hope the idea is clear. Here, of course, we'll have m by v, m1 v1 by m2 v2, but of course the mass is same, right? The planet at point A and B is the same planet, right? Mass is same, so v1 by v2, and that in terms of r1 by r2, since the options are in terms of r1 and r2. So at point A, what is the angular momentum? It's p cross v, right? So, or mvr we can write mv, and what is the perpendicular distance? So v1 we have, and perpendicular distance is r1. So you'll see that it's inversely proportional, right? v1 and r1. So here also you'll have m v2, and this is the perpendicular distance. So r2, about sun we are finding. Okay, about sun it is conserved. So here m and m will get cancelled. So v1 by v2 is r1 by r2. So sorry, r2 by r1, right? Inverse relation. So here also v1 by v2 is r2 by r1. So the correct choice for the ratio of momentum is r2 by r1, which is option C. So that was the concept that we had to use in this question. Over to the next one. Question 6 and 7 over here. In question 6, we are given the radii and the density for two planets. Okay, you are supposed to find the ratio of their acceleration due to gravity. Okay, so now only we have discussed, okay, that gm is gr square, so gm by r square gives you g, right? So mass is directly related to density, right, and it's inversely proportional to r square. Okay, wait, so mass, you have to write it in terms of density into volume. Volume is 4 upon 3 pi r cube, and here you'll have r square, right? So this r square cancels with this, so you'll have basically g is proportional to rho and r, right? So their ratios g1 by g2 will be, so once you take the ratio, this constants will cancel out, right? So you'll have only rho 1 r1 plus divided by rho 2 r2, or rho 1 r1 is to rho 2 r2, which is option C. Okay, so simple application of this formula that I asked you to remember. Okay, it's useful to convert your escape velocity, right, in a better format. Okay, so here we have a planet of mass m, mass which is equal to that of mass of Earth. Okay, then its radius is 1/4 of that of Earth. You are supposed to tell the escape velocity. Okay, so here escape velocity, now they have not mentioned explicitly that it is from the surface, but in cases such, they are meaning that if not mentioned explicitly that it is from the surface of the planet, you consider it to be from the surface of the planet. Okay, so that is what your NCERT tells you. So here we know the formula from the surface. We'll write it in this format. Okay, useful one, as I have told you, this formula. Okay, so now escape velocity of the Earth is this. Right, now for this planet P, we have the same mass, so same mass m, but the radius is 1/4, r by 4. Okay, so it is in the square root, so that will become half. So first of all, we can bring this 4 on top. Okay, we can bring this like this, right? It is root 4 r by 4, so that comes on top. I can write this entirely like this, right? So r by 4, that 4 comes on top, and this 4 can be removed from the square root sign, so you'll have 2gm by r, which is of course the escape velocity of Earth, right? So which is 2 times, so for the planet it is 2 times that of the Earth. Okay, so basically the radius has become 1/4, so it will have higher gravity at the at the at the surface, right? So it will require, for this planet, it will require higher escape velocity, so 2 times the escape velocity of that of Earth. And here they have not mentioned the escape velocity for Earth, and you are supposed to know such values, especially for BITSAT. Okay, so it is 11.2 kilometers per second, okay, for Earth. So here 2 times that, so 22.4 kilometers per second is the value of escape velocity for this planet, option B. Okay, so that's about these two questions. Over to the next one. Let's discuss question 8 and 9 over here. In question 8, we have a planet which is revolving around a massive star of radius r. So orbit radius is r, and if the gravitational force of attraction between the planet and the star is inversely proportional, so this is of use. So this is inversely proportional to r to the power 3. So I can write f is equal to k r to the power minus 3, right? So k is some constant. Okay, so then we are supposed to find the period of revolution around the planet is proportional to. Okay, so now we are supposed to find the time period, right, which we can write as 2 pi by omega, right? And forget about 2 pi, since we are supposed to find the proportionality, we have to find omega somehow. Okay, now this force which is making the planet go in the orbit is the centripetal force, right? It is providing the centripetal force, so m omega square r will be equal to this force. So gravitational force, basically you equate it to the centripetal force, m omega square r, right? mr omega square. Okay, so here from here you will get what will happen. So we'll get a relation for omega. So r can go on the other side, and it will become r to the power minus 4, right? Or k also we can take it to the other side. So this is r to the power minus 4. So omega is proportional to, so this k and m are constants. So omega as a power of r is proportional to r to the power minus 2. You take square root on both the sides, right? So omega is proportional to r to the power minus 2 and t is proportional to 1 by omega. So this means t is proportional to r square, right? It is proportional to r to the power minus 2. So 1 by omega, that is proportional to r square. So t is proportional to r square. Now in place of this 3, you can take it in general r to the power n, and you can do the same exercise. That will give you the answer to one of your BITSAT previous year question. Okay, so you can try that out. Let's come to this one. Here we have a satellite of mass m revolving around the earth, circular orbit, radius r, angular momentum L. You are supposed to find the potential energy. Okay, so simple, right? Gmm by r with a minus sign. But here we are supposed to find it in terms of angular momentum. Okay, so this is a peculiar question. Since we have done this, now it can click you that you can use, like, if you want potential energy, it is Gmm by r, right? And we are given angular momentum. Okay, how can we reach angular momentum? We can use the concept of centripetal force, right? Somehow, somewhere. Okay, so basically your force will be Gmm by r also, right? Or let's take the magnitude r square. Okay, so here L will be, what is angular momentum? It's mvr, right? So from here, what can we do? We are supposed to express this in terms of this. Okay, this in terms of angular momentum, u in terms of L. So from here we can find, now since it is the centripetal force, gravitational force provides the centripetal force. So mv square by r. So I'm writing it in terms of v now, linear velocity instead of the angular one. So we have like this. This is r square. I'll use capital R only, or small r. Okay, fine. So this and this will get cancelled. M does not depend on the mass of the body. So velocity is under root g m by r, right? Yes. So this velocity you can substitute over here and try to obtain u in terms of L. Okay, so we'll substitute v because we see v nowhere, right? We see v nowhere. So there is no v, so I'm trying to do that. Okay, I'm substituting v to get rid of v, and that will lead us over here. Okay, so that is the idea. So gm by r, and okay, so we want gmm by r, right? So gmm by okay, so can we square this on both sides? Since you can see L square, right? So we'll get gmm, m square also will get okay, so where is this m square coming from? Okay, so we'll have m and r, right? So m, v and r. Okay, so now we can square it on both sides. So L square, so I'm squaring this, equal this on both sides. So m square, r square, and we'll have gm by r. Okay, this and this can get cancelled. So we want to find g and L square by so I want to form this. Okay, so I'm taking gmm, I'm keeping over here, and I think I should have kept this r because we need gmm by r, right? So this is r square. So I'm bringing this m square, r square over here. Okay, I'm bringing only one of the m's. Okay, so here, so I get the form gmm, right? 1m I'm giving it to the right hand side, 1m I'm bringing it over here. Okay, so now also we have r, this r, right? So this is the form. We want potential energy, just put a minus sign and we are good to go, right? So potential energy, take negative on both sides. So potential energy is nothing but minus L square by m r square. Okay, and which is option D. You can see that. Okay, so this is the way to obtain it. Okay, and actually you could have neglected out certain options like this one and I think this one. They are dimensionally incorrect, right? You can also go by the process of dimensional analysis and compare the dimensions on both the sides. This will not be equal to potential energy. This also won't be equal to potential energy. Only this forms, right? This and this differ by constant. They are potential energies, so you could have taken a guess. But yeah, Doing it correctly is better than taking a guess. That's about question 8 and 9. Over to the last question for the day. Question 10 over here. In question 10, we have a satellite of mass m orbiting the Earth, which has radius r, and the satellite is at a height h from the surface. So this total is r plus h from the center. So h from the surface and r on to the center, right? So here we are supposed to tell the total energy of the satellite. Now for a bound system, you'll know that the total energy is same as kinetic energy, at least sign wise. Okay, total energy is negative. It's a bounded system, and total energy is half of potential energy. Okay, so it works out. Okay, so it might seem awkward that potential energy is 2 times the total energy. It happens so because kinetic energy is positive, potential is negative. So if you add those, it will decrease, right? But still it will be something negative. So total energy comes equal to kinetic energy. Sign wise it is opposite. Okay. Anyways, we are just supposed to compare these two. Let's not confuse you with the kinetic energy at the time. So 2 times the both have negative signs, so no need of this now. So that mod was necessary for kinetic energy. So 2 times T will give you U. Okay. So total energy we are supposed to find, right? So we can do basically this only we can use. T is half of U, right? U we know. U is minus GMM by the distance, right? The distance from the center. So R plus H. GMM by R if the satellite was on the ground, but here it is at a height h, of course. So it is R plus H, right? So that is the potential energy. Now in terms of G we are supposed to find, but before that let's have total energy. This will be half of potential energy, so GMM by 2R plus H. Okay. Now to obtain in terms of small g, you know the form GR square is GM, right? Capital M. This is the mass of the planet in this case, the bigger mass. Okay, planet, or in case of planet orbiting around the sun, it will be the mass of the sun. Okay, so bigger mass. So here Gm will be replaced by Gr square. So mgr square upon, so here they had actually given G naught. Okay, so we will use G naught and divided by 2R plus H. Okay, so you just had to use this concept, and your answer, if you can see, this is not negative. Okay, this is interesting. Let me check. Okay, this should be square, and this is correct. Okay, yes. So option B is your correct choice. Let me brief you up about also the escape velocity concept. As I told you that it is not always under root 2 gr. It's only root 2 gr if it is from the surface, right? So basically the concept of escape velocity is that you equate the final energy to 0. So initially you'll have some kinetic energy, so you'll give some mve square, so that it escapes the gravitational potential energy of the earth, which is gmm by r. Okay, at the surface it is r. Okay, here if you have some other length 2r, if you want to make it escape from that distance will come over here. Okay, so that this becomes 0. Now if you solve, you'll get that relation, ve is equal to under root 2 gm by r. You can see m and m will cancel, small m, and you'll get this relation, right? So it is only, and this is if of course equivalent to saying under root 2 gr, right? Because gm is gr square, and you can do the algebra. So escape velocity is under root 2 gr if your object is escaping from the surface of that planet. Okay, it won't be root 2 gr, the distance will change over here, some factor will come, right? So if we have 2r, the 2r will come over here. If you are making it escape from a distance of 2r from the planet, that distance will come here. The concept is you equate the kinetic energy due to the escape velocity, and you cancel it out basically with the gravitational potential energy. So that final energy becomes 0, and you get the escape velocity. Okay, so you equate the kinetic energy to your gravitational potential energy, the value. Okay, so that was the concept of your escape velocity. It's not always under root 2 gr. Be careful of that. So I thought there was a question which was there coming up next, which will explain this, but sadly there was none. So anyways, just for the completeness, I've told you the concept now. So that's about today's video. I hope you really enjoyed it. I'll see you soon. This is the last video for the year of 2024. I hope you enjoyed the content this year. Give it a like and subscribe um, if you align with the vision of cracking BITSAT 2025. So I'll come around next year with the same enthusiasm and the same goal, and we'll be continuing with the question bank series. We'll get some more content for BITSAT 2025, the strategy and all the mock test series or the Super 30 series. Will bring it back, and um, we'll try to crack BITSAT 2025. Okay, so that is the aim. I'll see you soon in the next video, hopefully next year, and till then keep enjoying physics and keep watching my videos.